Area between curves using vertical rectangles. Our objective is to demonstrate how to find the area between curves when functions are defined in terms of x, the independent variable. Some materials for review include definite integrals and their evaluation and properties of definite integrals. Some terminology. If f and g are continuous, with f of x greater than or equal to g of x throughout the closed interval ab, then the area of the region between the curves y equal f of x and y equal g of x from a to b is the integral of f minus g from a to b. So the definite integral from a to b of the quantity f of x minus g of x dx is equal to the area between the curves. Our first example has a graph where we have y equals square root of x and y equal x minus 2. The orange region is the region between the two curves. To find the area of this region, we use the following integral. We take the integral from 0 to 4 of the square root of x minus the quantity x minus 2. And this is set up because square root of x has larger y values than x minus 2 over the region from 0 to 4. They cross at 4, and we start our variable of integration at 0. Evaluating this integral leads to the result of 16/3. And notice that the function with the larger y values is listed first in the subtraction. Suppose we have two functions that cross over each other within the interval. How does this affect the evaluation? And our next example details the situation. So the graph on the left is the graph of f of x, which is equal to 3x cubed minus x squared minus 10x. Our second graph, g of x, is negative x squared plus 2x. And we can see from the graph that from negative 2 to 0, f of x is greater than or equal to g of x. But from 0 to 2, g of x is greater than or equal to f of x. So here we have a point inside the interval negative 2 to 2 where the graphs change roles, where one was bigger than the other. So how do we handle such a situation? Well, to find the area between these curves, we're going to use the additive property of integrals. So graph the two functions on the same set of axes. If the intersection point occurs within the closed interval you are considering for integration, find these intersection points by solving the equation f of x equal g of x. Use the additive property of integrals to rewrite the definite integral from a to b of f of x minus g of x dx to a pair of integrals that you're going to add together. The first integral would be from a to c of f of x minus g of x, and this is used when f of x is greater than or equal to g of x. And then you're going to add on another definite integral from c to b of g of x minus f of x. And again, this integral would be used where g of x is greater than or equal to f of x. And c happens to be the x-coordinate of the solution to where f of x is equal to g of x. Evaluate each of these integrals to obtain the total area between the curves. So you evaluate the integrals and add them up. So for our example, first thing we do is we figure out where f of x equals g of x. So we have 3x cubed minus x squared minus 10x is equal to negative x squared plus 2x. So we go ahead and combine like terms using properties of equality. We have 3x cubed minus 12x equals 0. We can factor out 3x to have 3x times quantity x squared minus 4 equals 0. X squared minus 4 is the difference of squares, so we factor that accordingly. And we have 3x times quantity x plus 2 times the other quantity x minus 2, and all that's equal to 0. So now I can set each factor equal to 0 and solve, and I get x equals 0, x equal 2, x equal negative 2. And these are the intersection points between f and g. Now we're going to set up and evaluate the integral. So the integral from -2 to 2 of f of x minus g of x dx can be split apart into the integral from -2 to 0 of f of x minus g of x. Now, in this case, this is going to be 3x cubed minus x squared minus 10x minus the quantity negative x squared plus 2x. That's going to be integrated with respect to x. And then we're going to add the integral from 0 to 2, where g of x is bigger than f of x. And this would be negative x squared plus 2x minus the quantity of 3x cubed minus x squared minus 10x. Remember, you have to take away the entire function, all terms. So now we go ahead and perform this simplification, combining like terms, having a simple integral to evaluate. And we have -2 to 0 of 3x cubed minus 12x squared dx. We're going to evaluate this integral. And we have the integral from 0 to 2 of -3x squared plus 12x dx. The antiderivative of 3x cubed is 3/4 x to the 4th. The antiderivative of 12x is 6x squared. So we're going to evaluate that from the difference of those two terms from -2 to 0. We're going to do something similar for the second integral to go from 0 to 2. Performing the arithmetic, we get negative quantity 12 minus 24 plus -12 plus 24. And when we simplify all of this down, we have 24 as the result. So the area between the two curves over -2 to 2 is 24. Thank you for your time and attention.